Hi everyone, in the last video we looked at expanding binomials of various powers, and we expanded a plus b to the power of 0, a plus b to the power of 1, a plus b squared, etc., all the way down to a plus b to the power of 6. We saw that there was a pattern in the coefficients of all of these binomials. The pattern is that all the coefficients formed this triangle. This triangle is called Pascal's Triangle. This triangle is called Pascal's Triangle. We discovered that any term in Pascal's Triangle can be calculated as the sum of the two terms immediately above it. So what does that mean? Well, this term is equivalent to the sum of the two terms immediately above it. Another thing to note is that all of the first term in each row, we'll call these the rows of Pascal's triangle. The first term in the row and the last term in the row are always ones. And notice that here we have that this term is the sum of the two terms immediately above it. And so is this term. So 3 can be represented as the sum of 2 plus 1. And so we get this additive pattern. And this is incredibly useful because it's really quick to come up with the entries in Pascal's triangle, and then we can use the entries in Pascal's triangle to expand binomials, because we know that the coefficients when we expand binomials are going to be the entries from that row in Pascal's triangle. So a couple things to note here is that these are the rows of Pascal's triangle. So we actually use row number, we let n represent the row number, and this would be n is equal to 0. So this is the 0th row of Pascal's triangle. N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6. So those are the row numbers. Now, so let me just draw that out. Actually, this is the 0th row. This is the row number 1. This is row number 2. This is row number 3, row number 4, row number 5, and row number 6. And the next row would be row number 7. And if you're wondering why we say that this is the n is equal to 0th row of Pascal's triangle, it's because that matches the exponent when you expand a plus b to the 0. And then the n is equal to 6 row, when n is equal to 6, that row will correspond to the expansion of a plus b to the power of 6. So if I go to the row n is equal to 6, and I look at the entries, all of those entries correspond to the coefficients when you expand a plus b to the power of 6. So that's why we use this numbering system. And then we can also come up with the diagonal numbers. The diagonals look like this in Pascal's triangle. So let me use a different color. This is the diagonal that corresponds to r is equal to 0. We use r to represent the diagonal number. So that's diagonal number r is equal to 0. This diagonal here is diagonal number r is equal to 2. This diagonal is diagonal r is equal to 3. This would be r is equal to 4. This would be r is equal to 5. Whoops, I think I missed one. So, oh yeah, I did miss one. Okay, so, sorry, this is actually r is equal to 1. I skipped from 0 to 2. So this should be r is equal to 1. This is r is equal to 2. R is equal to 3. R is equal to 4. R is equal to 5, and this would be diagonal r is equal to 6. So notice that here it says any term in Pascal's triangle, can be calculated as the sum of the two terms immediately above it. And then it also says we can represent a term in Pascal's triangle by its row number n and its diagonal number r. So what that means is that if I wanted to represent this this entry in Pascal's triangle, so this entry, let me use a different color for that actually. Let's use red because it's easy to see. If I wanted that entry in Pascal's triangle, well, I could represent that as term T sub n is the row number, so it's row 2, and that would be diagonal 1. So that I could represent that as the term T sub 2 comma 1. So we can actually build Pascal's triangle using the term numbers. So for instance, if I have, if this is, the first term would be in row number 0, diagonal number 0, would be T sub 0, 0. And then this would be T sub 1 comma 0. This would be T sub 1, 1. And this would be T sub 2 comma 0, T sub 2 comma 1, T sub 2 comma 2. And this would be T sub 3 comma 0. T sub 3 comma 1, T sub 3 comma 2, and T sub 3 comma 3. Next we'd have T sub 4 comma 0, T sub 4 comma 1, T sub 4 comma 2, T sub 4 comma 3, and then T sub 4 comma 4. Okay, so each of these terms can be represented by the diagonal number, or the row number n and the diagonal number. So that's why we use this notation. Okay, another thing to note is that there's a pattern, because there's this additive pattern, and any term in Pascal's triangle can be calculated as the sum of the two terms immediately above it. If I have T sub n comma r, where n is the row number and r is the diagonal number, well, that's equal to the sum of the two terms in the row above it. The sum of the two terms immediately above it in the triangle. So that would be, the row above it would be T sub n minus 1, comma, this term is, if, like, let's say I wanted to calculate T sub 3 comma 1, it would be equivalent to this term, which is in the diagonal before, in the row before. So that would be T sub n minus 1 comma r minus 1. And I'm going to have to add to that the term in the row before it with the same diagonal number. So if its diagonal number is r, the same diagonal number would just be r. So for instance, let's see here. If we wanted to calculate, if we wanted to figure out what T sub 4 comma 2 was, if I wanted to rewrite T sub 4 comma 2 in another way, so this is the number in the with row number 4, diagonal number 2. Well, that would be equivalent to T sub 3 comma 1 plus T sub 3 comma 2. And if we check in Pascal's triangle, is it true? So we followed this formula, and is it true in Pascal's triangle? Well, let's go to the entry in the fourth row, or not the fourth row, the row number 4, diagonal number 2. So row number 4, diagonal number 2 is right here, and it's going to be the sum of this term and this term, which is what we've wrote here. So this is another way. If I have in Pascal's triangle, if I have the term in the fourth row or not the fourth row number 4, diagonal number 2, I can write that as the sum of the two terms immediately above it. And likewise, if I'm ever doing some arithmetic with Pascal's triangle, and I have the sum of two terms that are the sum of two adjacent terms in the same row, I can write that as a single term in the next row of Pascal's triangle. So that's something that can be useful at times.